These videos will assume practically no previous knowledge and will end with a description of advanced signal processing. We'll take broad conceptual steps along the way. I think the videos could be useful to students looking to get an overview of the material before taking a signals course, or students looking for a review before taking an advanced signals course. Since we're assuming no previous knowledge, our first step will have to answer the question, what is math? Math is a language constructed to model the physical world. Math attempts not to contradict itself. The reason I'm emphasizing these points about math is that one of my principal difficulties in learning signal processing was accepting things on the basis of definitions. Internalizing new mathematical definitions requires an acknowledgement that math is just a constructed and flawed language, and not some essential truth. We emphasize the fact that math attempts not to contradict itself because there will be several cases when our intuition is just plain wrong, and the only way to convince ourselves of the validity of our arguments is to prove we are not contradicting any mathematical definitions. The next question we need to answer is, what is a variable? A variable is an abstraction used to generalize. As an example, let's find the area of a rectangle which has one side of length 3 and one side of length 5. To find the area, we multiply the two sides, and the result, 15, is the area. We can find the area of a rectangle given any two sides, and it's quickly evident that we can make the general case that side 1 times side 2 is equal to the area of the rectangle. Our general case summarizes what could be an infinitely large table of values into a single equation. That's the power of variables. A variable can be represented by anything we like. Usually we use single English or Greek letters, just to be quick about it. The next question we need to answer is, what is a function? A function is a set of operations on an input that results in an output. The input goes into our box, a set of operations are done to the input, and the result, the output, comes out. When we consider the input, the function, and the output all at once, we are describing what is known as a system. Looking back at our example of finding the area of a rectangle, we described two inputs, represented here by the variables b and h. The output is represented by the variable a. The function consists of the operation of the two input variables b and h being multiplied. We will be concerned mostly with single input systems in these lessons, so we will make the variable h equal to the constant 3. Our new system consists of an input, variable b, an operation, 3 times b, and an output, variable a. Often, the set of operations of the function are too cumbersome to write inside the box of our system, so we represent it by a letter, f in this instance. The representation of the function is followed by parentheses in which we specify the variables on which the function will do a set of actions. We call the variable on which the function operates the argument of the function. When we do not wish to specify a particular variable, we often leave the argument as a dot. So far, we viewed the system as an input going into a function and an output coming out. What if we tried reversing the direction? Let's look back at our rectangle system. Our input b is passed to the function. The function multiplies b by the constant 3. Our output variable a is assigning the result. The system can be thought of as a representation of an equation. So another way to say the same thing is to say f of b is equal to a. F of b is just the operation 3 times b. We know that all we have to do is write in the value of b, our unknown side length, and the result will be the value of a, the area of the rectangle. But what if we know the value of a and want the value of b? We isolate the variable b by dividing both sides of the equality by 3. Now we translate our equation back into system form, and we can see that the functions to go from b to a and a to b are not the same. It's important to note that the reason the functions are not the same is not because we wrote a b inside one box and an a inside the other. When we write systems, the variable inside the box can be represented however we like, though we often keep it the same as the input so we can follow our own logic. A change in the direction of the system requires a change in the function. We describe our new function as the inverse of our original. and represented by the superscript -1. For the functions we care about, the operations of a function are cancelled by the operations of an inverse function, and the order does not matter. If you're not convinced, prove it to yourself using our example system. Finally, we need to introduce the concept of spaces. A space is a theoretical construct to contain a set of values. A function relates two or more spaces. We call the space of the input the domain. Said another way, the domain is the space that consists of all values which x can take. The range consists of all values which y can take. A function shows the relationship between the domain and range. When we make plots of functions, we are just illustrating how the values of a domain and the range are related. For two-dimensional plots, the domain is usually plotted as a horizontal axis and the range is plotted as a perpendicular vertical axis. Let's plot our example function, with one side fixed at 3. It's often easiest to calculate a few sample points and create a table of x and y values before plotting. Note that if the input is less than 0, area just doesn't make sense. So x less than 0 is not included in the domain. We then plot our sample points and draw a line through them, indicating the relationship. The line we've drawn indicates that both x and y may take any positive value greater than 0. We will now be describing the difference between discrete and continuous functions. Whether a function is discrete or continuous relies on whether its input variable is discrete or continuous. I haven't been able to find any succinct definitions of discrete versus continuous variables. In my head, I say that if a variable can take an infinite amount of values, it is continuous. If a variable is limited to a finite amount of values, it is discrete. Then I add to this the addendum that this does not consider the limits. Let's say that the variable x takes values between -infinity and infinity, and that the variable y is equal to the variable x. We then plot a few points showing this relationship. If x can take an infinite amount of values between our sample points, it is continuous, and the function is represented by a line. If x is limited to a finite amount of values between sample points, it is discrete, and the function is represented by a scatter plot or stem plot. In summary, mathematics is a language. A variable is an abstraction used to make generalizations. A function defines the relationship between an input and an output. An inverse function undoes the operations of a function. An input, function, and output considered together form a system. The domain and range of a function represent all the values which the input and output of the function can take, respectively.